Ever wondered how artificial intelligence deciphers the meaning behind human language? It's not just about recognizing words. It's about encoding semantic relationships in a way machines can process. Today, we're exploring a groundbreaking technique that leverages mathematical frameworks to revolutionize how AI interprets sentences. Let's start with the foundation. In natural language processing, words are typically represented as high-dimensional vectors called embeddings, mathematical representations that encode semantic and syntactic properties. But sentences, they're far more complex. Traditional methods either oversimplify by collapsing structure or become computationally unwieldy. This is where wavelet transforms and discrete cosine transforms, DCTs, offer a fresh perspective. Wavelets act as mathematical microscopes, allowing us to analyze data at multiple scales. Imagine dissecting a sentence by zooming in on local word interactions or stepping back to grasp global context. This multi-resolution analysis captures both fine-grained dependencies and overarching patterns. Meanwhile, DCTs, commonly used in signal processing, decompose signals into frequency components. Think of it as isolating individual harmonics in a musical chord. The researchers combined these tools to address a critical challenge, converting variable-length sentences into fixed-size vector representations. Here's the innovation. They first applied wavelet transforms to compress word embeddings, retaining only the most significant coefficients. This reduces dimensionality while preserving semantic integrity. Then they used DCTs to encode positional information, ensuring the relative order of words is maintained. It's akin to compressing an image by retaining key features while preserving spatial relationships. The results? Their method achieves efficient compression without sacrificing performance. On benchmark tasks like sentence similarity measurement, it matches or outperforms established models. Crucially, it's non-parameterized, no additional training required, making it computationally lighter and more adaptable. Why does this matter? Consider real-world applications. Chatbots that grasp context better, translation systems handling syntactic complexity, or search engines interpreting nuanced queries. By repurposing techniques from signal processing, this work bridges gaps between traditional mathematics and modern AI. So the next time you interact with an AI, remember, beneath the surface, it's using tools like wavelets and DCTs to decode meaning. Thanks for watching. If you enjoyed this deep dive, subscribe for more explorations into the cutting edge of AI research.